In this video, we're going to practice a little bit of our sugar terminology. So here is a starting sugar. What terms does apply to this sugar? What naming conventions would be applied here? And what stereochemistry conventions would be applied here? Pause for a moment, see if you can think of them. All right, if you're back, well, naming-wise, we don't need to know the unique name for this sugar. That's not part of this class. But we do know that it is 1, 2, 3, 4, 5 carbons in length. This makes it a pentose. Additionally, it has an aldehyde group as its functional group, so it is an aldose. In terms of the stereochemistry, we can find that there are 3 chiral centers. 3 carbons that have 4 different things attached. And while we don't tend to write them in often, don't forget that the other side is always a hydrogen. It just gets cluttered as we start making more advanced molecules, and so we will leave those off. But do remember, those aren't methyls in this case. That other side is always a hydrogen parallel to the OH. Well, I've got right, left, right for my OH pattern. That last chiral OH is on the right. This is a D sugar. Exactly which pentose this is, if we wanted to name, just for fun, this is xylose. And so this is really D-xylose. Now, you won't need to know that the unique name for the ABA pattern on a aldose is xylose. But if I wanted to draw L-xylose, I can use this information to figure out that molecule. In fact, take a minute. Draw L-xylose. Well, if you're back, I have my carbon. That's an aldehyde. I don't actually need to flip it left and right because it's not chiral. The left and rightness doesn't matter for carbon 1. But it will matter for carbon 2, 3, and 4. If I am still xylose, but I'm L, my last chiral OH must be on the left. Well, to have the same name, I must be mirror images of each other. Remember, the mirror images of sugars have identical names except for D and L. We tell you which handedness it is based on that last chiral OH. And so here's L-xylose and here's D-xylose. If I had this molecule, it is again a pentose, it's an aldose, it's a D-aldose. However, it is not xylose. I have an OH on the left. Hey, I had an OH on the left. I have an OH on the right. I had an OH on the right. But the pattern for xylose would demand I go back to the other side. I don't do that. The pattern on our new molecule is ABB, where on the old one it was A, B, and then back to A. And so start on one side, move to the opposite, move back, versus start on one side, move to the opposite, stay on the opposite. By having a different left and right pattern, we are a different named sugar. We can still determine that we are a pentose for being 5 carbons, and aldose for having an aldehyde for a sugar, and that we are D because our last chiral OH is on the right. Just for curiosity, this is arabinose. Again, you will not need to know the name for that specific pattern. So in terms of a Fischer drawing, we can actually learn quite a bit about it just from recognizing how many carbons, what its functional group is, and what is that last chiral carbon's direction. Take a minute, draw me a hexose, ketose, L sugar. Just any of them. All right, back. Well, if I'm going to be a ketose, I can't have my carbon double bond oxygen on the end. That would make an aldehyde. So it's going to be one in from the end. That's 2, 3 carbons, 4 carbons, 5 carbons. I need 6 carbons for being a hexose. The last one is not chiral since it has 2 hydrogens, but these other 3 in the middle will. And the top, number 1, it's not chiral because it has 2 hydrogens. So 1 and 2 are achiral, 3, 4, and 5 are chiral. If I'm supposed to be an L sugar, then my OH must be on the left for my last chiral OH. The other ones could go wherever you want, left or right. I'll just put them both on the right. Key was this one is what made it L. And so we have a ketose hexose that is an L sugar.